Math 1342, Section 1.3, Experiments and Observational Studies, Video 2, Confounding Variables. In the previous video, we discussed the concept of association and the concept of causation. But as we saw, there are some instances where there might be an association between two variables without necessarily having one cause the other to change. In other words, association without causation. Kind of makes you wonder, why would that happen? We saw a couple of instances of association without causation before. And we kind of discussed the possibility of what's called a confounding variable, a third variable that might be causing two other variables to respond. Let's just quickly recap what those two scenarios were. One of them was data clearly shows that weeks when lots of salt is used also tend to have more accidents. Should we cut down on the amount of salt we spread on the road so that we have fewer accidents? This was in the context of really cold and icy roads. So does that make sense that as the temperature drops, should it make sense that as we put more salt on the roads, that causes more accidents? In other words, is there a causation here? It doesn't make sense to say that adding less salt will cause less accidents, so there's no causation here. Cause less, not causeless. It doesn't make sense to say that adding salt will cause less accidents, so there's no causation here. However, when the temperature lowers, explanatory variable, there is more salt spread on the roads, response variable. Also, when the temperature lowers, there are more accidents, another response variable. So instead of saying the salt is the explanatory variable and the accidents is the response variable, it kind of makes more sense to say that the change in temperature is the explanatory variable, whereas both the amount of salt spread on the roads and the number of accidents are both response variables. And the other situation was families with many cars tend to also own many televisions. Does this mean if you buy a television, you will get more cars? Are we saying that we have a causation here? And the answer was no, we didn't. But is there a third variable that might justify the association between these? And the answer is yes. No, buying a television doesn't cause you to have more cars. I really thought I proofread this. However, if you have a higher income, explanatory variable, then you might buy more televisions, response variable. Also, if you have a higher income, then you might buy more cars, another response variable. So another instance of two variables that seem to have an association: number of cars you own, number of televisions you own, but not causation. The causation is associated with a third confounding variable, in this case, your income. Confounding variable. A confounding variable, also known as a confounding factor or lurking variable, I will always call it a confounding variable, is a third variable that is associated as an explanatory variable with both the two other response variables. A confounding variable can offer a plausible explanation for an association between two variables of interest. It is worth mentioning that confounding variable and lurking variable are technically two different things, but at this stage of statistics, we can pretty much treat them as the same. We're going to take a look at one more example: vehicle registrations versus life expectancy. And to see this example, we're going to go to the PDF of the second edition of this textbook. As soon as I can get it over there. There it is. Excuse me. Here's a table from the book that lists the number of vehicle registrations in millions and the life expectancy. I'm assuming of U.S. citizens. Obviously, the population not stated here, but we'll take the population of choice. And we have these registration numbers and life expectancies for years from 1970. It looks like it's going up by 4 years, all the way to 2010. What do you notice about each column? The vehicles and the life expectancy. They both seem to be going up. If we were to do a scatter plot, which is just putting a bunch of dots on a coordinate plane, here's the vehicles in millions, here's the life expectancy, and it seems like as one goes up, so does the other. From an algebra perspective, we would say that the slope of this quote unquote line is positive. So clearly there's an association. One goes up, the other one goes up. But is it a causation? Which is like asking, if there are more vehicles on the road, does that cause people to live longer, or vice versa? If people live longer, does that cause more vehicles to be on the road? And the answer to both is probably not. But what could be causing both of them to increase at the same time? The answer, it might be a little stealthy, but ironically, the answer is right in front of your face. The confounding variable is the year. Why? Well, what happens to a population of people as the years go by? The population gets larger. If the population gets larger, we have more people driving cars, therefore more vehicles. So as the year increases, that causes the number of vehicle registrations to increase. But how could the year increasing cause the life expectancy to increase? Well, as the years go by, researchers develop techniques, products, drugs, procedures that increase the life expectancy of people. And so as the year increases, the life expectancy increases as well. So it's the year that's serving as the explanatory variable. The number of vehicle registrations is responding to the year, and the life expectancy is also responding to the year. Now, it's not always easy to determine a confounding variable that would cause two other variables to respond and therefore have an association. But sometimes it is.